This is Applied Calculus, Section 4.2, Second Derivative in Graphs. We begin with a discussion of notation for the second derivative. If we have a function y defined to be equal to f of x, the second derivative of f can be found if it exists by evaluating the derivative of the first derivative. So we read this notation as f double prime of x is equal to the derivative of f prime of x. And other notations are stated below here. So we have d squared y over dx squared, or y double prime. These are other ways to say the second derivative. We want to apply this to the examples below. So if we want to find f prime of x, we would evaluate d dx of x squared, and this has us evaluate f prime of x as 2x. Now to find the second derivative, we would take the derivative of the derivative and get 2. We can do this also for g of x, but before we evaluate the derivative of g of x, we rewrite the square root of x as x to the 1/2, so we can use the power rule. Now the first derivative of g is 1/2 x to the negative 1/2 power, and the second derivative of g would be negative 1/4 x to the negative 3/2 power. To continue in this section, we talk about concavity. The graph of a function is concave upward on an interval AB if f prime of x is increasing on the interval AB. And the graph is concave downward on the same interval AB if the derivative of f is decreasing on the interval AB. So what this means is if f prime of x is increasing, this means the derivative of f prime of x aka f double prime of x is positive on the interval. And the interval we're looking at is AB. So for the interval AB, if f double prime is greater than 0, it is concave upward. If f double prime is less than 0, it is concave downward. And we see that they're using plus to represent positive second derivative, minus to represent a negative second derivative, and that plus means the first derivative is increasing, that minus means that first derivative is decreasing, and concave upward can look like any of these pictures here. It doesn't have to be a full semicircle, it could be a partial quarter circle arc, and concave downward is down below some images. So, concavity of graphs. Determine the intervals on which the graph of each function is concave upward and the intervals on which the graph is concave downward. Sketch a graph of each function. So we see that for the function f of x equals e to the x, it is graphed down below here. And we see that e to the x is concave upward for the entire domain. So we would say f of x is concave up for all x in the domain. And then next comes natural log of x, and we see that in this graph, g of x is concave down for all x in the domain. And for this last graph, we see that from the origin, it is concave down to the left, but concave up to the right. So h of x is concave up for x greater than 0. H of x is concave down for x less than 0. And we have a special name for this point here. The point at which a graph changes from concave up to concave down is known as a point of inflection. Theorem 1, inflection points. If the ordered pair C, f of C is an inflection point of f, then C is a partition number for f double prime of x. So our procedure for testing for inflection points, step 1, find all the partition numbers of C. Step 1, find all partition numbers C belonging to f double prime such that f is continuous at C. Step 2, for each of these partition numbers, construct a sign chart of f double prime near x values that are approaching C. And step 3, if the sign chart of f double prime changes its sign at C, so from positive to negative or from negative to positive, then C, f prime of C represents an inflection point of the graph of f. If the sign chart does not change signs at C, then there is no inflection point. So let's look at this here. We want to find the second derivative. And we want to set the second derivative equal to 0. And solve for x, and this is our partition. And we're going to create a sign chart around that. So we have x values, and then we have f double prime of x values. And I'm going to pick a number on the left of 2 and on the right of 2. This is our partition value, p. So when I plug in 1 into x, 6 times 1 minus 12 is negative 6. We don't need the exact, we just need to know, is it negative or positive? This is negative on the left side of 2. And if I plug in 3, 6 times 3 is 18, minus 12 is 6. Again, I don't need the exact, I just need to be able to determine if it is positive or negative. And since we see that the second derivatives are changing from negative to positive around x equals 2, that means we're going from concave down to concave up. It is a point of inflection. So there's a point of inflection at 2, f of 2. If we plug 2 back into the original function, we'll get the y coordinate that goes with it. So we get 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1. That gives us 8 minus 24 plus 18 plus 1. That gives us 3. So the inflection point is at 2, 3. So here's another example. Find the inflection points for f of x equals natural log of x squared plus 4. We will begin by finding the first derivative. So the derivative of natural log is 1 over the argument inside the natural log times the derivative of what's inside the natural log, so dx of x squared plus 4. And that's the chain rule that we're illustrating here. So f prime of x, we have an x squared plus 4 in the denominator and a 2x in the numerator. Now we want to find f double prime, and we should recognize that this needs the quotient rule. So the quotient rule says take the bottom function, x squared plus 4, multiply it by the derivative of the top function, which is 2, subtract the top function, which is 2x, multiplied by the derivative of the bottom function, which is 2x, and place all of that over the bottom function squared. Now we want to solve for when this is 0, and that will be our partition number, or for when this is undefined, and that can be our partition number. Before we do that, let's simplify the numerator. So now we want to take this simplified expression and set it equal to 0. And a fraction is 0 when the numerator is 0, so we simply need to solve 8 minus 2x squared equal to 0. And we get that x is equal to plus or minus 2, so that gives us 2 partition values. And next we want to say, is there a number for x that I can plug in that would cause a 0 in the denominator? That would be an undefined derivative, and locate a partition number. And we see that there's no number that we can square and get a -4. So the answer is no. These are the only 2 partition numbers we need to use then. We can create our sign chart, which will consist of x values and second derivative values. I need a value on the left of -2, on the right of -2, and that can be on the left of +2. So those are all the values I need. I know the second derivative is producing a 0 for each of these partition numbers, and I will choose -3, 0, and 3 for my other x values. Let's plug those into our second derivative, which is here. We don't need the exact value, we just have to reason as to whether or not it'll be positive or negative. This denominator will always be positive because anything squared is positive, plus 4 is positive, and no matter what that comes out to when it gets squared, it'll be positive. So the denominator is always positive. When I plug -3 into the numerator, -3 squared is 9. 9 times -2 is -18. 8 minus -18 is -10. So we get a negative in the numerator. And a negative over a positive gives me a negative. So this is what we mean by sign charts. I don't need to calculate the exact number. I just need to determine if that is a positive or negative value. Now we can do this again with 0. If I plug 0 into the denominator, I have 4 squared, it stays positive. If I plug 0 into the numerator, I get 8 minus 0, it's positive. And I have now a positive over a positive, which is positive. And then we can do this again with the +3. We know the denominator is always going to be positive, but when I plug 3 into the numerator, I get 8 minus 18 again, and a negative over a positive is a negative. So because we are changing concavity around x equals -2, that is an inflection point, and because we are changing concavity around x equals +2, that is another inflection point. So I have an inflection point at -2, comma. If I plug -2 into x, that gives me 4. So this is log of 8. And then if I plug +2 in, I get log of 8 again. So this is my answer for my 2 inflection points for this example. So on this slide, we are analyzing the graph, and in the figure, it shows the graph of the derivative of the function f, and we're going to use this graph to discuss the graph of f. Remember, this graph that we're shown is actually the derivative, which means that each of these ordered pairs are x and a tangent slope at x. So here I have a -5 as the slope when x is about -3.5. So someplace around 3.5, and it doesn't matter if it's above or below because it's saying a possible graph of f. There's going to be multiple answers, but I expect my graph to be coming in a downward direction because slope is at -5. And I see that as we get to -2, slope is approaching 0. So that gives it the possibility to either go up or go down from there. So we say, what happens after that area where slope is 0? Well, notice that the graph goes back into the negative. So instead of following the track up, it's going to continue going down. And then the slope reaches -2 and then starts to get less and less and approach 0. And that 0 happens at 1. So I'm going to say it comes like that. Now again, once I reach that 0 point, I say the slope can either go up or continue down. And when I look at this, now the y values are positive, which means the slope is positive. If the slope is positive, the graph must be making a turn up. And that's how the rest of the graph goes. So I'm just going to trace this with a heavier ink. And we see that we started coming down. We came to this point here that we thought we might turn up, but then it continues back down. And then we came to this point here where it was at 0 and it did turn into the positive. And this is a possible drawing for the graph of f of x. So here we have a set of guidelines for plotting points using derivatives to graph a function. Step 1, analyze f of x, find a domain and its intercepts. The x-intercepts are the solutions of f equals 0, and the y-intercept is f of 0. Step 2, analyze the derivative of the graph. Find the partition numbers for f prime and the critical numbers of f, and construct a sign chart. Determine the intervals where the graph of f is going to be increasing, decreasing, find local maximums and minimums. Step 3, analyze the second derivative, find the partition numbers, construct a sign chart, and determine intervals of concavity, where it's concave up and concave down, and locate any inflection points. Finally, you're going to sketch the graph after you've located intercepts, local maximums and minimums and inflection points, and all of the information you've acquired from steps 1 through 3, plot additional points if needed, and complete a sketch. Okay, so now we're going to apply the graphing strategy we just went over. And again, step 1 said to analyze. And to analyze, it states we should find the domain and the intercepts of the graph. So this is a polynomial function. We can say the domain is x, which belongs to all real numbers, or you can say x, which belongs to -infinity to infinity. And now we would like to find the intercepts. So we can start with the y-intercept. When we plug in 0 for x, we get 0. And then we can find the x-intercepts. First, we will factor. And we see we can factor an x cubed out of each term. Next, you set the factored equation equal to 0, and this finds that x equals 0 and x equals 2 are the values that will cause the function to equal 0, and that means we have 0, 0, and 2, 0 as our x-intercepts. Now that we've found the domain and the intercepts, we can go on and analyze the first derivative. So f prime of x is 4x cubed minus 6x squared. This is just using the power rule. Now we can find which values of x will give us a first derivative equal to 0. And we find that this happens at x equals 0 and at x equals 3/2. Now we can create our sign chart. These are our critical numbers, so we want to pick values on both sides of our critical numbers. And we want to plug them into the first derivative and determine if we get positive or negative outcomes. So when we plug -1 in for x, we get -4 minus 6, so that's a negative result. When we plug +1 in, we get 4 minus 6, that's a negative result. And when we plug 2 in, we get 32 minus 24, that's a positive result. So now we can say that f of x is decreasing for x in the interval from -infinity. So we see that it's decreasing from -infinity until we get to 3/2. And then we can say f of x is increasing for x in the interval from 3/2 to +infinity. And because we see it goes from decreasing to increasing at 3/2, this means that 3/2, comma, f of 3/2 locates a minimum, a local min. So step 3 in our graphing procedures says to analyze the second derivative. And that means we're going to take the derivative of the first derivative. And that gives us 12x squared minus 12x. And now we would like to analyze this. So f double prime of x can be factored as 12x times x minus 1. And we can see that x equal to 0 and x equal to 1 are the values that cause the second derivative to equal 0. So these are our partition numbers. And we can make a sign chart for the second derivative. 0 is one of our partition numbers. 1 is a partition number, so I need a number between 0 and 1. And remember, we don't need to calculate the exact value. We just need to determine if it will be positive or negative. So when we plug -1 in, anything squared is positive, and then minus 12 times -1 becomes minus a negative. So this will become a positive, just doing analysis of the signs. If we plug in 1/2, that gives us 1/2 squared is 1/4. 1/4 of 12 is 3. 3 minus half of 12 gives us a negative. And if we plug in 2 for x, we get 48 minus 24. That's a positive. So now we can say that f is concave up on the interval where x goes from -infinity up to 0, and union that with 1 to infinity. And I'm just looking at where I have pluses for my concavity, and I look at the left side of my plus. The left side of that first plus is -infinity. The right side of that first plus is 0. And that's how I got the first parenthesis for the interval. And then I find my next plus sign. I look to the left of that. I see the partition number is 1. And to the right of that, we go to +infinity. And now I will continue and say that f is concave down for x in the interval. And now I'm looking for where the concavity is negative, and I see on the left of that I have 0, and on the right of that I have 1. So for the interval from 0 to 1. So we see that there's a change in concavity at 0. There's a change in concavity around 1. Those are going to be points of inflection. And now step 4 of our strategy says to graph all of this information and draw a likeness of the graph. Okay, so let's put all of our analysis that we just did together so we can draw our graph. So remember, our function f of x is x to the 4th minus 2x cubed. This is the graph we are trying to generate. And we started this discussion by saying, well, what's the domain? And because it's a polynomial, we said the domain is x, which belongs to the set of real numbers from negative infinity to positive infinity. And the first thing we did was we said, well, let's find the intercepts. And we found that 0, 0 was an intercept on the y-axis. It is also an intercept on the x-axis. We found that 2, 0 was also an intercept on the x-axis. We found that the function was decreasing from negative infinity until we got to 3/2, and then it started increasing. So 3/2 is at 1.5. And we determined that there was a local minimum at the ordered pair 3/2, comma, f of 3/2. And if we plug this 3/2 into the f of x, we get a y coordinate that is approximately negative 1.7. So it means this would be approximately the location of our local min. And based on the first derivative, it's coming down the graph from left to right and then going up. And I just drew straight lines because I don't know anything about the curvature of the graph yet. That is where the second derivative comes in. So with the second derivative, we determined that we had partition numbers at 0 and at 1. So we have a partition number at 0, and we have a partition number at 1. And we said the graph was concave up from negative infinity to 0. And then it was concave down from 0 to 1. And then it was concave up from 1 through the minimum all the way up to positive infinity. Now, my concavities are very exaggerated just because I'm trying to show it. I still don't have the shape of the graph here, but I have the beginnings of the likeness of the shape of the graph. I see that this is a point of inflection because concavity is changing. I will call that POI for point of inflection. And here we have a point of inflection because concavity is changing. And now I would like to make this graph a little more precise. I don't really know anything about the left-hand side of this graph, left of 0, so we can pick a point and say, let me know where I should place a point at x equals negative 1. It's going to help give me some shape. So f of negative 1 gives us negative 1 to the 4th minus 2 times negative 1 cubed. This is 1 minus 2 times negative 1. This gives us 3. So that means the graph should be passing through this point. So I know it's coming through this point to this point of inflection. When it gets to this point of inflection, concavity changes back down and then back up through the minimum, back up through the x-intercept. But now I want to know, after it gets past this x-intercept, where does the graph go when x is 3? So I'm going to evaluate 3. So this gives us 81 minus 2 times 27. So from here we have a point 3 comma 27. So if I put a point for 3, I know that it's going to be really high up there, so I expect the graph to really go straight up. So now there's just too many lines here. I'm going to start erasing them. The red line was just to tell me that the graph was decreasing, then increasing. I'm going to delete that. The black line was to give me my initial drawings for concavity. I'm going to take those out. And what I'm left with is this green graph where I started to pick some points where I didn't have much information about the graph. And I now see that this is the shape of my graph that I have constructed. So if I put this function into the calculator, I expect to find something that looks a little bit like what I've drawn here in green. Maybe not 100% precise, but very close. So let's put this in the graphing calculator. We'll go to y equals. We'll type in our function, x to the fourth minus 2 times x to the third. Enter. Hit the graph button. And I want to get a better view of it. I'm going to hit the zoom button. I'm going to say option 2, which is zoom in. I'm going to move my cursor a little to the right and up, so I'm kind of centered there, and then hit enter to say zoom in on this point. And we say, wow, that looks kind of like the graph we just drew. So we have a pretty good representation of the graph of f of x, and we used a couple of intercept points, the increasing and decreasing analysis from the first derivative, the concavity analysis from the second derivative. We plotted the local min and the points of inflection, and then we looked at parts of the number line where we didn't know much about the graph, and we said, well, let's check out other values to plug in just to see how rapidly this graph is shooting up, or maybe it's going at a slower, wider growth level, and we got those points to help us get the ends of the graph look quite right. So here we have a maximum rate of change application problem. The problem reads that currently a discount appliance store is selling 200 large screen TVs monthly. If the store invests X $1,000 in an advertising campaign, the ad company estimates that monthly sales will be given by the following function. So this function is calculating sales for the month, and X is money in thousands of dollars. The question that follows states, when is the rate of change of sales increasing and when is it decreasing? So we have to read this carefully. Rate of change of sales is going to be n prime of x. But the question is asking when is the rate of change of sales increasing? So that means the rate of change of the rate of change of sales. And I take the time to write it out like this because you have to be able to identify that this question is asking for the second derivative. When is the rate of change of the rate of change in sales increasing? Well, that means when is the derivative of the derivative increasing? So this is a question for n double prime of x. So if we take n prime of x, we can use the power rule to find that it is 9x squared minus x to the third. And if we take n double prime of x, we get 18x minus 3x squared. Now, we want to know, when is this increasing? When is n prime of x increasing? That means, when is the second derivative positive? So we're going to find our partition values. We're going to create our sign chart. And when we create our sign chart, we have to remember that we have a domain that we're restricted to. So the left side of my domain is 0, but that's a partition number. I can't choose numbers on the left of that. There's no part of my domain that goes there. So 0 is my first value in the sign chart. I can pick a value after 0, and then 6 is another partition value, and then I can pick any value on the right of that, 7, 8, 9. I can even pick them all if I wanted to test them all. So if we plug 3 in to our second derivative, and if we plug it into the factored form, it makes it easier to evaluate. 3 times 3 is 9, 6 minus 3 is 3, 9 times 3 is a positive number. If we plug in 7, we get 3 times 7 is 21, 6 minus 7 is negative, positive times a negative is negative, and we see the same is true for 8 and 9. So the function is concave up from 0 to 6, but another way we can look at this is we can say the first derivative is increasing from 0 to 6. And the function is concave down from 6 to 9. But if we're referring to this in terms of the first derivative, we can say n prime is decreasing from 6 to 9. So we go back to the question, make sure we've addressed this. It says, when is the rate of change of sales increasing? Well, the rate of change in sales is increasing when $0 to $6,000 in advertising dollars are spent. And when is it decreasing? Well, when you're spending between $6,000 and $9,000. The next question is, what is the point of diminishing return and the maximum rate of change of sales? We find that the point of diminishing return occurs at 6 because we're going from the first derivative increasing to decreasing, and that would make that a local max for the first derivative. And since that is a local max, we would then say that is where the point of diminishing return is, and that the maximum rate of change would be n prime of 6. And then finally, they want us to graph n and n prime on the same coordinate system. So the last part of the question asks that we graph the original function n of x and its derivative n prime of x in the same coordinate plane. I'm at GeoGebra.org. I'm going to choose this waffle and GeoGebra Classic, and this is where I'm going to graph my function. And this is the input bar. I'm going to type n of x, because that's the name of our function, equals, and now I'm going to use a keyword function so that GeoGebra gives me a library to choose from. I have 3 options. I'm going to choose the one that gives me a starting and ending value for my function, because our n of x was defined on the interval from 0 to 9,000. Now I'm going to delete out the function in the first parameter and replace it with 3x to the third. Hit the right arrow after each exponent to drop back down to the base. And then I have minus 0.25x to the fourth. Now I'm going to hit the right arrow to exit the exponent again, plus 200. And now I want to go to the next parameter. I hit the right arrow. I can delete the parameter out and put 0. And then I hit the right arrow again and delete the parameter and put 9. And we see that everything is defined down below. I'll hit enter, and I don't see anything here for my function. I'm going to drag the screen over, and the reason for that is this function is at much larger y values than we have visible here. And if you were to plug 0 in for x, you would see that it would leave 200 as the y-intercept. So we're going to change the scale on this so that my y values is going to show values of 200 and higher. So let's come over to the menu here, choose settings, and then this circle and triangle is the graphics menu, and we're going to set up my x minimum to be at 0, my x maximum we'll put at 10, the y minimum we'll put at 0, and I know my y-intercept is at 200, but I'll put 1000 here instead, just to give it some room to move up and down. And then after I tab out of that, I see that I have my graph. I can see it now. So this graph goes from 200, it looks like it goes up to almost 750 on this interval. And remember, the problem defined x as being in thousands of dollars, so we're talking about over $700,000 in sales. Now we would like to also graph n prime, which is the rate of change in sales. So I can now, in my input bar, put n with the apostrophe for prime and hit enter, and it's done all of the work for me. Because n of x was restricted on the interval from 0 to 9, so will n prime of x. And I'm just going to change the color here. I clicked on the graph. I go to the graphics menu, and I can choose a different color. So it has a contrast with the two graphs. I have a red and a blue. Again, if you click on the graph, you can even change the line thickness if you want it to show up better or to print better. So I'm going to take a screenshot of this and put it into our notebook. So we see this is our n of x, this is our n prime of x, and we saw that 6 was the location of diminishing returns, and what that means is we've reached the local maximum for the rate of change in sales, and what that means is that sales, even though they continue to increase, they are increasing at a slower rate. So yes, sales continue to go up, but they don't go up as quickly. So we see that sales were flat down here, and the advertising dollars caused sales to start increasing at a faster rate, but then eventually the sales start to increase at a slower rate, and that's what this was locating for us, saying that this is the point of diminishing returns, that advertising dollars beyond 6,000 will start to yield less growth than advertising dollars before 6,000. So that is the end of this lecture. Go back, watch it again, take notes, and then go on and do the practice and bring questions to our next class.